Hello everyone, and welcome to Sky Scholar, the channel where you can learn about new concepts in physics and astronomy. I am your host, Dr. Robitaille. I am eager to talk to you about the solar spectrum, but first we have to cover blackbodies and the laws advanced by Wien, Stefan, and Planck. Then we will tackle Kirchhoff's law and finally get to the spectrum of the sun. In our previous video, we covered radiative heat transfer and Stewart's law. We also learned that the emissive properties of objects do not typically change with temperature in an easily predictable manner. But there is one class of objects where the emissive properties are closely related to temperature. These are called blackbodies, and they are the subject of today's presentation. Let's start at the beginning of the 1800s, even the late 1700s, and follow the line of reasoning outlined in my paper on Blackbody radiation and the carbon particle, which is linked below. In the 1800s, mankind had discovered that objects which are made of graphite or covered with soot or lampblack produced a very unusual type of light. These objects were different than any other objects, and they became known as blackbodies. As a result, the type of light that was produced was called Blackbody radiation, or normal radiation. But it would have been better called special radiation because there was nothing normal about it. The light or radiation produced by blackbodies was unusual because it was continuous, but more importantly, scientists could infer the temperature of the emitter by analyzing this light. Blackbody radiation was linked in an easily described and smoothly changing manner to temperature. No other radiative process in nature had this property. You can see the relationship of blackbody radiation with temperature in this figure. The horizontal axis represents wavelength of the light emitted in nanometers, which is 1/1000th of a meter. The vertical axis represents intensity. As the temperature of a blackbody is increased, the emitted light changes in a predictable manner. The position of the maximal emission moves to shorter wavelengths. This observation was formulated into a law by William Wien in 1896, which is known as Wien's Displacement Law. It states that the product of the maximum wavelength for the emission times the temperature always equals a constant, b, known as Wien's displacement constant. The equation can also be expressed in terms of frequency with appropriate changes in Wien's constant. In 1879, Joseph Stefan discovered something else about blackbody radiation. The area under the curve is equal to another constant, sigma, times the temperature to the fourth power. This became known as Stefans Law, and sigma is known as the Stefan-Boltzmann's constant. But it was not until Max Planck came along in 1901 that the full equation for blackbody radiation was formulated. Planck's equation described the shape of the blackbody curve in terms of only two variables, wavelength and temperature. Alternatively, Planck's equation, like Wien's, could also be expressed in terms of frequency. This is the central equation in dealing with blackbody radiation, and that is why it is so important. With the discovery of the equation for blackbody radiation, Planck became known as the father of modern physics. That is because Planck's law introduced the concept of the quantum, and the field of quantum mechanics was born. You can see the introduction of the quantum in the h-nu term. H is known as Planck's constant. H times nu became known as the quantum of action and represents the energy associated with a photon at different frequency. In addition, Planck's equation contains another constant, denoted by a lower letter k. This is known as Boltzmann's constant, and it has a precise value. It is related to the conversion of kinetic energy at the microscopic level to temperature at the macroscopic level. We will learn more about this when dealing with the second law of thermodynamics and the concept of order in an idealized system. For now, all you have to remember is that Planck's equation relates the intensity of radiation produced at a given temperature to either frequency or wavelength. Interestingly, you can derive both Wien's law and Stefan's law from Planck's equation using calculus. The first derivative of Planck's equation produces Wien's law, while the integration results in Stefan's law. Of course, everyone can know Wien's law and Stefan's law without ever learning calculus. You are now beginning to see why blackbody radiation excited the scientific community. Not only did it give rise to the idea that physics was quantized, but if you lived in the middle of the 1800s, you could also know the temperature of an object simply by analyzing blackbody radiation. But how was this done in practice? Scientists had already gotten into the habit of building cavities in order to study blackbody radiation. These were usually built from graphite, the same material found in a pencil. If the walls of the cavity were not made from graphite, they were typically covered with soot or lampblack, which was black carbon from the inside of oil lamps. This was one of the best absorbers. The walls of the cavity could not be transparent. They had to be opaque. A small hole was drilled into one wall to allow scientists to sample the light inside. To measure the temperature of an object, scientists inserted a few extra dividers in the cavity and placed a sample near a distant wall beyond the direct view of the small hole. After waiting for the temperature to reach equilibrium, the radiation inside the cavity could become black or normal, and the temperature of the object could be determined from the blackbody spectrum. The process could be repeated many times to ensure that the cavity temperature was adequately raised prior to the final reading. For example, the temperature of an object coming out of a hot oven could be determined with great accuracy by placing it inside a blackbody cavity, which was at thermal equilibrium with it. In this regard, it is important to remember that blackbodies tend to be heated cavities. For example, this can be achieved by placing them in a heated oil bath or by devising some electrical means to raise their temperature. In closing, remember the lessons learned so far. Different objects typically emit radiation, which has an uncertain relationship with temperature. But this is not the case for blackbodies. These objects are special because they have a strong relationship between their temperature and the light that they emit. We also learned that this relationship can be described by the laws of Wien, Stefan, and Planck. In our next video, you will learn about Kirchhoff's law. If you want to understand modern astronomy and its pitfalls, there is no more important relationship to learn. In the meantime, I hope that you enjoyed this video on blackbody radiation and some of the laws of emission. If you did, please leave a like. In addition, subscribe to join me as we look more closely at the sun, the stars, and beyond. Comments are always welcome down below. I'll see you soon on our next video.